Hi everyone. In this video, you're going to learn about vector-valued functions. But before we get to that, let's just talk about vectors in the plane. So the physical world is filled with applications of vectors. Vector applications appear in economics, computer graphics, and even statistics. And I'm sure you've probably dealt with them in a lot of your science classes. So first of all, a quantity is considered a vector if it gives us two things, direction and magnitude. So an example of a vector quantity that you're familiar with is velocity. Remember, the sign of velocity tells you the direction that the object is traveling in, and it also tells us how fast the object is moving, or the speed. Okay, so it gives us speed and direction. If the quantity is not a vector quantity, it's considered a scalar quantity. So speed, for example, is a scalar quantity because it only tells us how fast the object is moving. Some other examples of scalars are temperature, area, mass, and time. Okay, so the geometric representation of a vector is basically a ray or directed line segment. The starting or initial point P is called the tail or base point, and the terminal point Q, indicated by the arrow, is called the head, tip, or terminal point. Now, I tend to like to use initial point and terminal point because we use those same words with the unit circle, so we're just familiar with those. In most textbooks, vectors are represented by boldface lowercase letters such as U, V, W, or maybe A and B. So to notate a vector, we notate the vector by its initial point and terminal point, and so we may indicate vector V is equal to the ray PQ, where P is the initial point and Q is the terminal point. Okay, so the magnitude or length of V, which is denoted with this symbol, measures the distance from point P to point Q. All right, component form of a vector. If V is a vector in the plane whose initial point is the origin and whose terminal point is AB, then the component form of V is given by, and we use these pointed braces, and the coordinates A and B are called the components of vector V. If both the initial and the terminal point lie at the origin, then V is called the zero vector and is denoted like this. Okay, magnitude of a vector, which remember is just the distance between the initial point and the terminal point, basically can be found using distance formula. All right, let's look at an example. Given vector V, which equals ray AB, where point A has the coordinates 3, 7, and point B has the coordinates 6, 5, we want to write the component form of the vector AB. So to do that, to find the components, we are just going to subtract the x coordinates, so 6 minus 3, comma, and then subtract the y coordinates, so 5 minus 7, and so the component form would be 3, comma, negative 2. All right, so then to find the magnitude, we're just going to use distance formula. So the magnitude would equal the square root of 3 squared plus negative 2 squared, which would equal the square root of 9 plus 4, which equals the square root of 13. Okay, to sketch vector V, or ray AB, then we will just plot the initial point, which is at 3, 7. And we will plot the terminal point, which is at 6, 5. And then basically you're just going to draw a ray and put an arrow at the end. Okay, now to translate the vector v, the idea is if we were to just move this vector, let's see if I can just do this without having to redraw it. To translate the vector v, we're just going to translate it so that the initial point is at the origin. And in that case, you can see that your terminal point actually ends up at the point 3, -2. Okay. All right, so what is a vector value function? Well, it's just a function that is given by vector values. It's very similar to parametric equations. Here's an example. Okay, limits, differentiation, and integration of vector value functions are performed component-wise. So, for instance, if you're given the position vector at any time t, then to find the velocity vector, you would just find the derivative of x of t and find the derivative of y of t. And then to find the acceleration vector, you just find the derivative of the velocity vector for each component. All right, here's an example. A particle moves in the xy plane so that at any time t, the position of the particle is given by x of t and y of t. Find the velocity vector when t equals 1. Okay, so I would say here that v of t would equal x prime of t, comma, y prime of t, which would equal 3t squared plus 8t, comma, 4t cubed minus 3t squared. All right, then we can say v of 1 will equal 4 times 1 cubed, plugged into the wrong component. Let me just erase that. Okay, v of 1 would equal 3 times 1 squared plus 8 times 1, comma, 4 times 1 cubed minus 3 times 1 squared. And then if we work these out, we will end up with 3 plus 8, which is 11, and 4 minus 3, which is 1. So the velocity vector when t equals 1 is this. All right, find the acceleration vector when t equals 2. Well, your acceleration vector, or a of t, is just going to equal x double prime of t, comma, y double prime of t. All right, so that's going to equal 6t plus 8, comma, 12t squared minus 6t. All right, and then a of 2, now we're just going to plug in 2 to each component. All right, so that'll end up giving us 6 times 2 is 12, plus 8 is 20, comma, and then 2 squared is 4 times 2 is 8. 8 minus 12 is -4. Okay, now these formulas probably look familiar because we use these also with parametric equations. So remember to find the speed of the particle, which would also represent the magnitude of the velocity vector. You find the square root of either dx dt squared plus dy dt squared, or you could think of it as the square root of x prime of t squared plus y prime of t squared. And then to find the length of the arc, or the distance traveled by the particle from t equals a to t equals b, we just integrate that square root. All right, here's an example. A particle moves in the xy plane so that at any time t, where t is greater than or equal to 0, the position of the particle is given by x of t and y of t. Find the magnitude of the velocity vector when t equals 1. Okay, so first of all, we have to find the derivative. So we're going to find x prime of t, which is 2t plus 3, and we'll find y prime of t, which is 3t squared minus 6t. And then we're going to plug in a 1. So x prime of 1 equals 5, and y prime of 1 equals negative 3. And then to find the magnitude, we will find the square root of 5 squared plus negative 3 squared, which will equal the square root of 25 plus 9, which equals the square root of 34. And so that would be the magnitude of the velocity vector when t equals 1. All right. So as you can see, these actually are not that bad. They're very, they are essentially parametric equations because we're still dealing with x and y, both as functions of t. In a way, we're really just kind of writing them in a little bit different format when we write them as components. So, all right, you guys. Well, we'll definitely practice this some more in class. As always, thank you for watching, and have a good night.